Okay, hello everyone. Today we have Rob Deere from Vrije University to talk about valuations of p-adic.
Welcome, Spencer, just in time.
Can I see?
Hey, so first of all, let me thank the organizers for the opportunity to speak here. Secondly, in the abstract, I actually put in or sent for the email around that from Coates, so it's not about me, but this is joint work with Tejaswi Navilarekallu, which was with me in Amsterdam some time ago. What I'll be talking about was actually 2016, as you'll see from the years and some of the slides, and the speed at which this field develops. That was yesterday. Okay, so we get here. It started with us getting interested in a paper by Coates and Lichtenbaum, Annals 1973, where they formulated a conjecture, which is I think more general than one will be published by Lichtenbaum sometime before that. Of course, they also published some cases, so they proved some cases at stage already. So let me also, well, they set up, you take an odd prime. So totally real number fields, when it is okay, an even arcing character, realizable over 2p. It doesn't have to be one dimensional, it could be higher. So maybe two dimensional or something like two dimensional reducible. Some primes, find for the primes, including primes above the prime number p, and also everything where character is verified. And then, okay, we do a little trick, they do a little trick. If you look at a negative odd n in that case, and the character I should say so is even, so every complex conjugation in the Galois group of k bar over k is going to act trivially. So in that case, if you choose actually a map from 2k to p to the complex numbers, then you can write down this particular alpha. Sorry about the notation, the k is maybe at the end, and the n is at the beginning, the variable. And then there's a theorem of Siegel that this will be in the field about which your character takes values. And then you can choose a reverse map on the image of QP and C back to QP. And that gives you then a way of interpreting what should be maybe a complex number as actually an element in QP. It's going to be non-zero and it's independently getting shot. So this gives you a way of viewing at least at particular points the values of those L functions, the classical L functions being in the p-adic field that you start with. And then, well, there's several ways of formulating this conjecture. I sort of took the easy one because that's the one that works to prove it and the more general version of this. So you start with a five-dimensional vector space V, on which you actually realize the representation underlying the character. You then choose the stable ZP subletters of this vector space, and then you're going to create the torsion quotient. And depending on which thing you look at, or you can look at either this one or you sort of dualize, in which case you get maybe non-torsion coefficients and different indices for your cohomology groups. Anyway, so the simple formulation is what I've written down here. So you look at the étale cohomology groups of where you localize your images to S, so you invert a particular prime P and every prime of O, where chi is ramified, you give your torsion representation here a nice Tate twist, and then you hope that all those cohomology groups are actually not finite and trivial variety is equal to 2. And then the other thing that they conjectured was that if you now look at this multiplicative Euler characteristic, which of course by the first part should involve only A0 and H1, then this is just going to be some power of p, and it should be exactly the p-adic absolute value of this p-adic interpretation of this L function. Okay, so they provide some evidence in this paper already. And some years later, Bayer-Neukirch proved, well, effectively the simplest case. So the character there becomes trivial. We still have an odd integer n, And they at that stage assumed the main conjecture of the Iwasawa theory, which was then proved by Wiles about 10 years later. So in that case, they actually go for a p-adic function. And so this, well, depending on your station, this p-adic function could be a branch of the p-adic zeta function that I prefer to write it like this for this Title character that's introduced here. So if you look at your cyclotomic character for the p e-power roots of unity, then, well, you can always split this, of course, into the Title representatives. So you project this one down to the roots of unity in there, that using the Title representative, that composition will be the Title character omega p. And then the other thing is actually something that is very close to, well, let me actually notice that I will be using PS2 later, and then PS2 likes to be an exception. And therefore, if you take the other parts of the diamond part, people are close to home, p-adic. Okay, so you get this L function, and then they actually show them the HI as 0 for I is to be to the 2, so you only get the H0 and H1. They're well finite, and you have the correct interpretation, right? So with a trivial character, so the space V is just 2p, stable Z module ZP submodule ZP, and you get exactly this one. And then you're now in a p-adic world. Right? This is a p-adic function, but then there's an interpolation formula which will show up in the next slide or something like this. And then you actually see from that one that the value that was in the Coates and Lichtenbaum conjecture, the value will be exactly the same as the one up there. And so this proves that conjecture in this particular most elementary case. And as far as I can tell, that was essentially the situation that people will never look at this thing again after this. And so say this really became a result after Wiles proved the main conjecture of the Iwasawa theory, but that is essentially for all. So let's review some p-adic functions. So we fix a prime p, as I said before, I will include p equals 2, which tends to drop out in the Iwasawa theory because it's harder. And then you take the cyclotomic ZP extension of K, and then, well, you also have then the mu2p roots of unity to, if you join those to K infinity, you get full cyclotomic P extension of K. So then so going from this sort of finite extension of K, and so you're going to the P through the unity if P is over plus or minus I if P is 2, you go up this ZP extension, and then you choose to generate it there, and that one will then be close to 1. If you identify this Galois group with, well, the total Galois group K infinity mu to P over K is now inside ZP star, and then you've chosen this ZP, which is now close to 1 modulo P in this representation. So the result is that if you take any P power roots of unity, then this element that you take as a generator will x by raised to the power of 0, which is close to 1, and this makes sense. Even, so this makes sense p-adically if you expand to 0. Okay, and then the way you can actually get this L function, this p-adic function, by substitution in a power series. So what you do is you take this Q0, and then you're going to raise it to some p-adic number. And usually people take in a Z or in a ZP, but if you look at it closely, you actually see that this makes sense for every element being to be large, that p-adically is so sufficiently close to 0. The important thing is that if I take Q0 to, say, this power S, then the exponential function involved should converge. In particular, it will actually include ZP, which will be good enough for Coates and Lichtenbaum. So how are you going to generalize their conjecture? Well, you're going to take a character and representation. So we're first going to extend the field P to something bigger, find the extension E. And then we're going to stick to even arcing characters. First of all, one-dimensional of the Galois G K bar over K. And then many people have shown there's a unique way of creating a p-adic L function with domain this whole dk, such that it actually satisfies this interpolation formula. Right, so again, well, we've seen the type of the character here, and as again before this now a p-adic character, but the setup is such with the parity of chi and parity of n that if you write down your classical L function here, because you embed e into the complex numbers, you get some non-zero number in the image, and then you take the inverse image back to the original copy of e. This will be independent of your choices. Right, so then there's a way of p-adically interpolating this. But by the way, note this shifting between the character chi here and then the twist with the typing of the character in the sort of the classical. Okay, so you can actually see from the Iwasawa theory, sorry, not from the Iwasawa theory yet, you can actually see there is a neater way of getting those p-adic L functions. So they're going to be effectively given by a power series with coefficients in OE, the valuation ring of this finite extension E of QP, divided by a polynomial with coefficients in there. So more precisely, it looks as follows. You have some power of the uniformizer, power of pi. You have distinguished polynomial, so this is something that is monic. And apart from the leading coefficient, every other coefficient lies in the valuation ring. And then you have a unit in the power series ring. So that simply means that the constant term will be a unit. And then it's also a polynomial that depends on the specific character. So it's one dimension at this stage. So either you take it all to be one, or if you have something, a character that factorizes through a finite extension of finite part of your cyclotomic power, then you get a root of unity times equals 1 minus 1. Then you divide by that one. So this is, if you take a trivial character, this will be the polynomial t, so infinity becomes 1, and that will result in presumably a pole of your p-adic L function at 1. If you don't have a trivial character, then this will not have any zeros in the domain of p-adic L function, so you will not have a pole. Anyway, so then you can interpret your p-adic L function in this way. So the power of the uniformizer, then your distinguished polynomial, and then you plug in q0 1 minus s minus 1. So this will be close to 1 p-adically. Then you get something that will always be a unit, here, and then you divide by this. So it's polynomial, because this 0 1 minus s minus 1 is close to 1, close to 0 p-adically. And the way I set it up is such that your s, you can certainly do this for s is p, which can be a little bit bigger in general, because q0 is close to 1 p-adic. And then once you have actually, once you have your p-adic L function for the interpolation formula, you can then go through the machine of Vrije induction to see that you can get a p-adic L function for any character, and it will have a similar interpolation formula for the negative integers with the correct parity set. So the other ones, because the local Euler factors compatible with the sorry, I don't say this yet. Okay, so you have this for every even outing character at that stage, and then so Greenberg actually also shows before Wiles proved the main conjecture that if you have this main conjecture, what happens if you're going to do Vrije induction on things like this, you're going to get quotients of this. Of course, the units together will form a unit, and then you're going to get two quotients of distinguished polynomials. And then Greenberg basically showed that if you do this, then there will be cancellation. You get essentially no denominator, except for if you have one of those characters you start with. Okay, so this means that if you do this like this, then you may get the G chi, if you do it for a random, for an arbitrary character chi, the G of another chi used in the Vrije induction could maybe end up in the denominator. And Greenberg says this doesn't happen. The only thing that you'll show that will be exactly the things for the one-dimensional characters you start with. For example, if you have a irreducible two-dimensional character, this distinguished polynomial and the denominator will be 1. Okay. So that means, as I said before, the only way you can get a pole for your beta function out of one of those H's is with a trivial character inside your beta character, and then you must be looking at s equal 1. Okay. Yeah, so let's then look at the main conjecture of Iwasawa theory a bit. So let's go back to our one-dimensional even arcing character with a bit more notation. So now we have factorizing this thing to finite extinction k over capital K over little k. And so we assume this thing lies nicely with respect to the sigmoid ZT extension, right? This goes in one direction and the capital K goes completely off in another direction. And what you can do is you first take the compositum of the two. So you go up your sigatomic tower from little k to little k infinity, and you take your compositum with capital K. So in that case, you have actually you have also the k infinity. To go from little k to little k infinity, or to go from capital K to capital K infinity is basically the same Galois group here on this assumption. And from there, you then go to L infinity, the maximum will be the entropy extension of this k infinity unramified outside lines of P and the infinite times. So that's the Galois group L infinity over k infinity is the one that one really studies in this kind of, say, classical Iwasawa theory. I should also say there are two ways of formulating this. I've sort of taken away the easy one, because I am going to look at stuff that is unramified outside P and the infinite primes. You can also sort of take a dual version, in which case the parity of your chi has to change from even to odd. You get a twist of the technical character to the power -1, I think. And in that case, you consider only unramified extensions. And then again, this one seems to be a little easier to handle than the other one, which people may like more for applications. Anyway, so you can, from Iwasawa theory, you actually know that if you take your Galois group X, right, so this is a prototype thing, well, of course, the group at the bottom, in particular the ZP from the sigatomic extension, will act as a group at the top, and therefore this will become a module over the ZP from the Galois group from your sigatomic ZP extension, but also the end will still act on it, and it will commute. And then, well, the main objective, the main projector is basically this one. And then, okay, so this one should really view as the x tensor of ZP with OE, but then take the part where n, capital Nx through the character time. That's basically eigenspace or eigensub OE module. And then it's actually known that you can describe its structure up to a finite co-kernel by injecting it into a bunch of OET, power series modulo powers of P, which I think, excuse me, should have been the uniformized pi by now, as well as quotient of this one by some distinguished polynomials. And then this is if I assume that P does not define the order of n. And if you are in that situation, well, then you replace OE with capital E everywhere, so this becomes 0. And this becomes, well, somewhat less controllable. Anyway, so Wiles actually, so the main conjecture tells you that if you look at the L function, p-adic L function that we associated to chi in this one-dimensional case, was this distinguished polynomial G of chi. And then the first thing is that the G of chi should be exactly the same as a product of the Gj that show up here. That's one thing. And then secondly, also, I think I'm afraid I have some typos here. So this should be an I, this should be an mi. So the sum of those mi is the original exponent of pi in the p-adic function, which incidentally is supposed to be 0 if pi is odd. And something like the degree of your field extension if p equals 2 in this case. Okay, so Wiles proved this one, and we will actually only use it in the case where this basic extension n of k is of order prime to prime p, and for p equals 2, you assume exactly this case. I should also say that we formulated in this case for p odd, but Wiles actually does prove part of this conjecture also for p equals 2, for example, as k is q in some other cases. So there's a little bit more than what I want to put on the slides at this stage. Okay, so we were happily trying to prove those Wiles for more arbitrary characters. And then we actually realized that what happens if you have the state twist and you want to do something with some fields, in order to have the state twist, you need the sqrt character. So you're essentially forced, because you already have your ZP extension and your sqrt ZP extension. And in order to interpret the state twist, you basically also have to join the two brief rules of unity. And then if p is odd, this is sort of harmless, because you first take something of degree dividing p minus 1. You work there, and then you try to go back to your original field by doing Galois descent, where all the coefficients are p torsion with the group for the prime to p. So this is easy, a bit of waste of time, but for p equals 2, this goes horribly wrong, because all the coefficients are 2 power torsion, but then you have to join I, an extension of b2, and then your descent becomes a spectral sequence, and it becomes horrible. We tried everything that it doesn't work, it becomes very complicated. But it actually turns out you can just work around the problem, and then you don't even see the difference between p equals 2 and not prime. So, as I say, we have this sqrt p power character, which we can decompose using the title character, and this one here, the diamond character, which is close to 1, p-adic. And then, if you actually manipulate this enough, you start to realize that the only thing you're doing is you're struggling with this guy here. The example, if you look at the interpolation formula for the classical p-adic zeta function, you have a congruence condition modulo p minus 1, and this p minus 1 is simply exactly the order of this character. So at some stage, when you decided it would be much easier is to just get rid of the entire thing and get rid of our headaches. So instead of twisting by this one, and here you're effectively forced to take integer twisting powers, we're going to twist by only that. Okay, and this is going to be close to 1 p-adically, and therefore I can raise this one to a p-adic number, provided it's not too wild, right? And that's where the decay earlier shows up. So we're going to simply, if we have any module over the Galois group like this, then we're simply going to use this diamond twist instead of the Tate twist. So I'm trying to make a case, because I thought you maybe a modified Tate twist, but I'm hoping vaguely that this will be called the Navilarekallu modified Tate twist, but I suspect this may not catch on like this. Anyway, so once we figured this is the way to go, we could simply include p equals to every variable. In fact, you need 1/3 of what we'd written until then, because most of this stuff was struggling with this omega p. So this is one of the main things I want to make here. So if you were p-adically use this diamond twist rather than the Tate twist, which is unnatural in the p-adic world. Okay, then another thing that we need for Coates and Lichtenbaum, remember we actually had not taken the full p-adic, the full L function, we had thrown away some Euler factors, we truncated the thing. So if you want to do this p-adically, you also have to do it like that. So this is the p-adic L function, so for all the primes that we have, and then we throw away some finitely many Euler factors, but you also have to be a little bit careful how you do that. Because this would be, say, the normal Euler factor that you define for another field. And then, well, if you want to get your interpolation right, you have to not quite take the same thing. So you get something like a diamond Euler factor, which shows up in other places in the literature as well. And then instead of the norm of your prime that you plug in for your Euler factor, you actually get a diamond. Then at that stage, you have to throw in omega p minus 1 to get it to get exactly the right interpolation from. So once you've done that, you've now expanded your interpolation formula from the full L function, full p-adic L function to the truncated ones. So again, you get the same kind of formula before. Again, if I go from the p-adic world to something that is from the classical world with this omega p and minus 1. Okay, so in the process, you've used Brauer induction. If you're careful, then you notice that for negative n, this makes sense everywhere because you only have non-zero numbers, and for n equals 0, you have to be more careful because some of those people could actually be 0, and then you lose the information if you're taking quotients. Okay, let's move on a little bit. So remember in original Coates and Lichtenbaum, they had an odd prime number, and they conjectured that H2 and up would be trivial. So again, with P=3, you have to be a little bit more careful because one thing that they choose is they choose some subletters in their vector space realizing the presentation, but there's no unique way of doing it. If you have another one, if you want to compare them, you get a finite quotient. So if you do that, you end up in this kind of game. You get étale cohomology or continuous group cohomology with coefficients in a finite module. Right? So this is the kind of ambiguity that is defined, that is inherent in the definition of the Euler characteristic, and you have to get rid of it. And again, for P is all this is easy because this will truncate here, but for P=2, it will actually continue indefinitely. So you need a little lemma, namely if you are having finite modules, say, with order invertible in the ring that you start with. For us, all those things will be P power and we inverted P. And for example, complex conjugation X strictly on those AI, which is also the case for us because we have well, the representation that we start with, the character involved is even, so complex conjugation X strictly there. And because we use a diamond twist, because the Tate twist, this will also kill the action of complex conjugation because you only see this through the typing character, and that is something we remove. Okay, so in that case, if you were to write down your long exact sequence of cohomology for 3 finite groups like this, and we go on indefinitely, actually it turns out you can truncate it right here. And the reason for that is not very simple. So it's known for a group like this that we have that this H3 and up is basically dictated by the Galois cohomology of what happens at the infinite primes. Of course, then you get worse Z modulo to Z for this one, so it's going to be shift by 2. And then because the action is trivial, this is the same as a home, right? Or even simpler. I could stop here, I think, because we've been assuming that if I now replace my H3s, that will be on the next time with H1s. Then I could come in with the H0s, and this is now subjective because this is a copy of H2, this is a copy of H3 values. And so you can just, for example, really nicely, you can just truncate your order characteristic there. Okay, so that means we are still on board with the order characteristic for finite modules for P=2. And then it is, well, sort of well known almost in p-adic cohomology that if I have a finite GF module and I'm going to compute the truncated Euler characteristic, then H1, the size of H1 is the product of the size of H0 and H2. And so that means that if I actually do what I sketched before, I take a representation realizing my character, I choose some submodule, some subletters, and I take a different one and compare, I get sort of basically a finite quotient. And then if I look at what I get from the Euler characteristic of my finite quotients, that will be 1. So that means the Euler characteristic I define on these lattices will be independent of the chosen lattice. Okay, so let's now go on to the more general case. So we have an even character of this double GK to some finite extent E of QP. And actually, let's assume that E is big enough to actually realize this thing on an E vector space. And then you choose your OE lattice, OE being the ring of the valuation ring, inside your vector space, and then you go to again create the torsion representation, so to say, like state V modulo. And then it turns out a little bit later, because we are now thinking heavily p-adically, but at some stage maybe we want to go back to the classical world, and then we want to replace our p-adic twist, the diamond twist, with the Tate twist on integer n. And of course, if you think about it, this contains the diagonal character to the power of 1 minus n, and also the diagonal character to the power of 1 minus n. And if I put it in here, then the action on left and right is exactly the same. So that will cancel that one. And the yeah, you should also realize that in that case, the vector space you can also use for either this one or this one, because it only uses values in ZP star, so this will act on anything without any problem. Okay, so as I mentioned before, if I do this construction for 2 different lattices and I want to compare them, I end up in something like this with a finite kernel, and then then to have finite homology in this one or this one will be the same, because this K will give rise to only finite homologies. Okay, so then we finally get the Euler characteristic. So as I said in Coates and Lichtenbaum, you would not see an H2, but for v equals 2 you might. And then we've modified the Tate twist. And then also because we being sloppy about the E, I may extend E, and then my cohomology will get bigger accordingly. Therefore, if I compute this thing, I have to then correct for the degree of field extent. So this will be the modified truncated v equals 2 Euler characteristic that we're looking at. And of course, assuming those homology groups there are finite. May also have to show that this H2, although it's in this formula at this stage, to keep it correct with the Euler characters of the finite modules. If you go to distortion coefficients, it actually turns out to be divisible, p-divisible. Well, it's always divisible by other primes, and therefore it's either going to be big. It's going to be some some dual of contracting dual or something like OP or bigger, or it's going to be 0. So that means that either you have a problem defining this, or the H2 will drop out in the end anyway, and it will simplify to only solve for Coates and Lichtenbaum, but then also for prime 2. Okay, so let me then formulate what comes out. So we have still the same situation, K total real P prime, E of QP finite, then an even character chi with values in E, and you can actually realize it through a representation over E, if you take E large enough. So you have to invert the primes above P, and also the primes of chi is ramified. And then if you take this E, okay, so this is now going to be the Tate twist, but no longer with an integer thing, but something in the p-adics, and with this diamond Tate twist, then you end up with the following. Okay, so you want to be too specific. You can also include equals 1, but you then have to be a little bit careful about the pole, the supposed pole of your say the zeta function as equals 1 or e equals 1. Anyway, you can see that the hi with this stuff is finite, except maybe for e equals 1, for I equals 0, and it is trivial for h3 and up, at least at p and odd. And then the well, maybe you should say start here first. So another thing you get here is an interpretation of your zeros of your p-adic alpha. And that you usually don't have, because people stick to maybe integer points that they calculate, or ZP, but of course the zeros of your distinguished polynomials to be outside. So this will actually interpret the zeros of your distinguished polynomials, at least coming from the image of the exponential map. Okay, because if that is going to be 0, then this is going to be infinite, and this is going to be infinite. And if you apply contrarian duality, you get something that is an OE module of finite ring. So if you want the rank of the dual, you use the co-rank of that one. So one thing that is very classical, at least with sort of maybe more normal twists, is that for the total new fields, so the Euler characteristic is 0, R1 equals R0 plus R2. And then one thing we actually can prove using the interpretation is that if you look at the order of your p-adic alpha function as point s equals e, then you get some estimate. So it's R2 minus R0 is minimum. So if you actually think, to interpret this, for most E, this R0 is simply going to be 0, so let's ignore it. So this is then the minimum of 1 and nu, this will be R2 and this will be nu. Okay, so for example, for nu equals 0, then this is 0, this is 0, before R2 equals 0. And then from this one here, also that one will be of 0 co-ring. And conversely, if this is going to be positive, then this will be at least equal to 1, and R2 will become positive as well. And so this is the kind of game you can play to actually see that those two things are equivalent. And then also, if your p-adic alpha function is non-zero as your p-adic thin E, then the formula that shows up in Coates and Lichtenbaum holds. But of course, here we have the p-adic alpha function and not the alpha. Okay, I also should maybe say that we could have quoted Wingberg to say that apart from E equals 1, there is never any pole, but we actually wouldn't make any difference. You get that back. But of course, Wingberg's result is stronger because we could basically, for us, we could have in the Iwasawa quotient of power series for the p-adic alpha function for a higher dimensional character, we could have some distinctive polynomial that has no roots in the image of the exponential map. And that would be okay for us, but Wingberg tells us that it cannot happen anyway. Okay, I want to just say one or two things about the proof. First I want to do Coates and Lichtenbaum. Okay, so as I said, what we have here for the theorem is this p-adic alpha function. But now switching back, so Tate is going to be the original character that shows up in Lichtenbaum. So then it has a certain parity, meaning every complex conjugation will act as minus 1 to the power 1 minus n on representation. And then you twist it with the correct power of typing the character to get a product chi, which is going to be even again. And then for the chi, we have this equality here, right? Because at least if we hope that the p-adic alpha function is non-zero, then we just show that the p-adic valuation of the p-adic alpha function raised to this thing here is going to be exactly the characteristic of this power to be exactly that. And that is entirely p-adic statements. And now you want to interpret that and say, well, I can do that. I can now go back to the normal Tate twist by actually putting in my power of my technical carrier into chi, and then I get the agent. That's the thing you see in the conjectures. And then also, if you go back to your interpolation range, you see the same thing happening. Right? So then you see that if you want to, this is your chi, the chi here, the alpha function actually interpolates this from here. You get the exact same shift of the with the typing character. Right? So I think I want to also make a case that really one should just think of all these entire things like characteristic p-adic alpha functions and twist as something entirely p-adic, and then you can interpret it for an integer in terms of the classical world of the Tate twist here. In the relation here, you get the exact same shift of the same power of the typing character. Right, and then because in the interpolation range then it's negative, this is non-zero, so that means that this is actually just a finite quotient. And then Coates and Lichtenbaum is simply the very simple case where you actually have a character, I think with values in 2p, I remember. And I think I should also have said in that case you have to have n, and I think n was odd. But even for qp you get a slightly stronger result. Okay, so I want to say slightly, just a little bit about this, about the proof, sort of long to get to this very general result. So that this thing is finite for I equals 0 is a little exercise. One thing I did not put on the slides, but is actually useful in the proof of this theorem, is that if you look at A0, H1 and H2, etc., then there's also a whole history about showing that this is co-finally generated, meaning the Von Vrije dual is a finally generated OE model. And I think Tate started this maybe, and there will be many things. And we also prove things like this. You get very general statements that co-rank of such things is independent of, well, the max you need only an upper bound for the co-rank, which is, I think, independent of little e, independent of capital E, independent of your realization. I think it only depends on your character chi, how you look, right? And I think this goes in somewhere because you want to change E and little e as well. Okay, anyway, so one is not so strange. This one I'll say a little bit more about because I think this is certainly new. And well, this was maybe not surprising, but certainly surprising with the E in the p-adic block. Okay, so say the first part of the scheme is standard. Then the second one you build up. So if you take the character chi one-dimensional and put it not visible by p, then that's exactly where you're in classical Iwasawa situation. And then our proof is not really very new because in that case you have a relation between the distinguished polynomial of your p-adic function and this group X that we talked about, or the correct part of it. And then if you just compute your A0 and H1 using this flows out quickly. That is sort of standard. And then the hard part was to actually get from there to an arbitrary character. So you first do some Brouwer induction where you only stick to one dimension, but you're going to sort of allow powers of P in the order. And then the interesting thing is because you can change E, if you have a character for the P, you're going to necessarily get ramification. So that means your field E has to get bigger if you start to with the small one before unmodified over P. And that means you can actually use complex conjugation. Sorry, you can use conjugation over an unmodified extension of P, and you can then compare with what happens if you do Brouwer induction. So that's how you get up to arbitrary one-dimensional characters. And then in the end, you also bootstrap yourself to Brouwer, using Brouwer induction to arbitrary chi. But what you actually prove in the first thing is that you assume that this holds. This will be automatically the case for almost all E because all those power series have only 20 many zeros. And then you really show that this implies this and this one. And so then what you have to do in the end is actually show that the converse holds. And then you have to be letting your E vary, and that's also the way you do that one. Yeah. Okay, so then actually, if you have an arbitrary E, well, if you're lucky, your p-adic function is already non-zero, and you can see what you want there. But then you have to really, if you have a zero, you really have to analyze what happens if you approach this using E primes, where actually your L function does not vanish, and you see what happens. But if I have a PL function that is going to have a zero at E, and if I get close, well, this wouldn't apply if this is zero. If E prime close to E, then the p-adic value of this one will blow up. And from the formula for the other characters, this means that this one is going to blow up. So we have to play a game, and that's also how you end up with this one. But by the way, one conjectures of any folklore that that this is actually inequality. This thing is to hold exactly, and you cannot prove that, unfortunately. It has to do with the structure I gave before, this one here. So if you know, and I think it may be even equivalent, that all those distinguished polynomials in the structure theory have no multiple roots, then I think you get exactly equality there. But the trouble is if you have a square here, say, it will not give you corresponding 0 or 2 for your p-adic function. You lose that information. Okay, where are we? Yeah, then I sometimes like to compute examples. So in this case, I maybe like someone else to compute examples because computing the L function is sort of non-trivial. So fortunately, Xavier Galois is very good at those for either basic Q or real quadratic Q. So that's what we get here. So I asked him to do some examples, and then he can do somewhere K will be little k will be real quadratic, and capital K will be sigma will be 4, And then the prime we use here is 5. So that means that we're in almost a simple situation. We don't go up to the higher part of the theorem. So we only have to invert the primes above 5. And then again, well, you can now see more explicitly this my pointer. That in this case is definitely a little bit bigger than Z5. Yeah, so again, the A0 is going to be rather boring here. So the only thing we're really computing is, well, A, if the p-adic function is non-zero, that the H2 is going to be 0, and then the side of the H1. So what he actually calculates is the approximation of the distinguished polynomial in the that gives you the p-adic function. So simple example, this quadratic field, and then the Hilbert class field A is to be 4, sigma to be 4 over this thing. And he finds in this case the distinguished polynomial is trivial. So that means that your p-adic function is this long. It could be a power of p, 5, but this is 0 in this case. And if we just have a unit in the power series ring, this always gives you p-adic value of z unit. So that means that, well, because A0 is already trivial, H1 will also have to be trivial. And if you then, well, you can put in your interest again, you get a more normal situation, and you get this one effectively. This p-adic thing is always trivial. Another example is in this case a ray class field modulo 5 over this quadratic field. And here he finds that this distinguished polynomial approximation is of E1, it's approximately t minus 5. But then in this case, you know, by looking at the interpolation formula, that actually it must be 0, 0. And it will mean that you actually know this distinguished polynomial exactly in this case, no approximation. And then you can actually calculate from the proofs that are hidden what the structure is, and then you simplify this one for the H1. Okay, then maybe one quick bigger one. So here your distinguished polynomial ends up being quadratic. And so this is a finite expansion. So this is basically 3 times 5 plus a bit smaller. And then this is basically 5 to fairly high 5-adic precision. And so this will be able to be useful, has no roots in Z5 at all. And you can simply calculate what this is. Still title here, the size of the H1 is always the same. It doesn't depend on your twist. And you can also calculate a structure. If you're in Z, and maybe if you maybe get close to the roots, it could actually change a little bit. So you really get some more information out of this before, and then you can actually then go up a little bit. Remember, we started with, in this case, a little from K. We go up the Z5, the sigma Z5 tower, and then we also have the big field K, which is before. And over this whole thing, we then have this maximal unramified row 5 extension or something like this. But this is starting from the quadratic number. And of course, you can also let the conjugation of that one act, and then the whole thing at the top will shift. So before, for example, in this example here, this Galois group X, or the correct part for the character here, and then maybe 1, because rank 1, because it corresponds to the distinguished polynomial. If I let the conjugation of the quadratic field for 1 over Q act, and I get another copy, so I get actually a 2-dimensional Galois group. And then you get, in this case, very explicitly the structure. So this is basically 2 copies of this thing, the part of X at the very top. At that stage, what will act will be, well, we started with the Galois group, the second Galois group was 4. And now we let it work over Q, and this group will be dihedral. Then we also have the sigmotomic Z5 extension, which we have now written like this for the normal action. So if you then figure out what's really going on here, you see that this one is X on this one by multiplication, so the way the whole thing was set up. And then the other one, the dihedral group, or 8 in this case, will act on the 2 copies of 5 using the irreducible 2-dimensional representation. So you can get some very explicit examples out of this one. And there's no approximation here. In this case, if you go to the third one, so in this case, the distinguished polynomials will be 2. So that means I have something Z5 plus Z5 at the top. that complex conjugation actually gets satisfied for the power 4. But you have to close it out by this polynomial to be not the way to do it. Okay, I managed to do this. No. Yeah, so we have to close it out by this polynomial. So it's going to be OE power series T closed out by this. It will be 2 opposite OE. But if you work it out, this quotient will just be this one. You join the square root of 5. It's the only thing you're doing. And then your T will act as one of the roots. So take a root like this, then you get this kind of funny action of this one, which is approximate because you don't know your PT exactly, you only know your PT tilde. Apart the same. So now we have, instead of rank 2 of such time, we have rank 4. Okay, so those were some explicit things you can get out of this. And then also, and this I think was actually maybe the reason for us to get into this. Neither I nor the postdoc working in Iwasawa theory, we rolled into this sideways. And to discuss a lot and be told a lot. So let's actually look at generalization of the Coates and Lichtenbaum conjecture, the equivariant Tamagawa conjecture. So people have been looking at this a fair bit, but usually only if your number field is abelian over Q. The reason is they sort of start with the K theory involved. In that case, if you want to write down elements in there, you basically need sigma units to get Benson elements there. And then people maybe be going through the functional equation. So that means that everything you're going to write down will be abelian, and you never get up to higher dimensional irreducible characters. I think maybe a lot of people have done that, but they have to make some assumptions that are stronger than the main conjecture of Iwasawa theory. So this is really without any condition. So that's negative n, and then the conditions here are such that I take a prime number p, and well, for p equals 2, again, in general, you have to assume it's part of the main conjecture of Iwasawa theory. Maybe not if k is q. Then you take a find a Galois extension for k that is either totally real, or you take it at CM field, and then you sort of project down onto the numeric part. There's a unique complex conjugation in the Galois if you have CM field, and you sort of look at where this one acts as -1. And then the statement is that, well, if you look at this motive for the equivariant Tamagawa conjecture, and we look at the rings of the maximal ZG order in 2G, then it will hold. And the way you prove this, you can actually do character by character in this case. And then again, the main point is the same as the Coates and Lichtenbaum. What goes in for the p part of this conjecture is actually the classical L function for this character eta, which I define here, right? So we and then using the interpolation, that will be exactly this, because the conditions mean that we are exactly where we can interpolate. There is K theory that corresponds to this point for the equation is going to be trivial. And then, again, as in Coates and Lichtenbaum, you can actually interpret this one through this p-adic twist using exactly this one. That's the exact thing that you need there, because effectively the conjecture will be similar to Coates and Lichtenbaum in this case. Also, I want to say, yeah, so actually one flaw that you may see in this argument, we do get away from the sort of the alt prime p and the reading characters that people usually consider as in this context. One thing that they might not like is that we take a maximal ZG order. Because that effectively means you do character by character, and people in Tamagawa number theory life would actually probably like to have any kind of the group ring or something like this. But that I think was out of bounds for us, and we definitely had enough with I should say the whole thing looks now very simple. We had a big struggle because at every stage you can basically decide whether you want to look at H0, H1 for the torsion, or you can dualize using computation and get something that is not so nice. In the applications, you actually often want to do that. You want to take our theorem and then dualize to get the application you have in mind. And with the advantage also of H0, H1 is they're much easier to handle using the Iwasawa theory than maybe the H3 and H2 that you can get with the dual coefficients non-torsion. And similarly, also, you can also take sheaves and then sort of push them forward to full ring. So E are not localized. But I think after a lot of struggle and resolving many problems, I think we found the correct point of view, which is this. Anyway, thank you for your attention.
Thank you very much. Beautiful. Are there any questions?
What does the equivariant Tamagawa conjecture say?
It interprets in this case the leading coefficient of the zeta or the leading, it's actually non-zero in this case, right? So at this stage we have the L function, I think it's exactly this, it's negative. Let's see. Yeah, okay. Right, so we actually need looking at this one here. And then normally this would involve you have some regulators, classical regulators, p-adic regulators for the K group, but there's no K group involved in this case, so this is trivial. So this is really essentially that's the I would say essentially boils down to Coates and Lichtenbaum. So you compare.
Ordinarily, the Tamagawa conjecture has to do with a sort of adelic volume or something. But it does say that this adelic volume is
yeah, but as I say, part of the volume will be coming from the p-adic regulators, right? Of the indication.
What my question really is, what is the ordinary Tamagawa is talking about the volume associated to adelic force.
Yeah, okay, but I think in the formulation that I have in mind is sort of long disappeared, and you get more something like a fundamental line, and you get some points in there, and then this is the exact statement. That
so this would sort of make Tamagawa turn great.
Well, I think this is sort of the version that Burns and Flach, right?
So
well,
why they call it Tamagawa?
Yeah, that I don't know. Maybe because in the end it started with Tamagawa, but actually I don't know because it's in the end it looks like. Well, I think maybe not Burns Lichten, but maybe Fontaine and Paramu were earlier in this game.
Yeah, they had a p-adic line.
No, actually, I don't exactly know why they call this Tamagawa number. Maybe because it was based on the Tamagawa number conjecture, and they have a group acting and it became equivariant. But maybe, you know, there are many things that are subtly misnamed, and I don't want to say it's the case here. But it's not impossible either. This is not 100%.
A really dumb question. The diamond twist is almost the same as the regular twist. Is it more than notation, or is it just?
No, it really enables the entire proof. So maybe, and this is actually one of the main points I would like to make with this talk, because if you look at the paper, Iwasawa theory basically almost immediately says that P be not prime. In fact, it took us quite a bit of effort to find the formulation of the main conjecture with our theory if the prime is 2, because everyone just ignores it. It's hard. So what really this is the thing. So here you have a circular character with finite order, and if p minus 1 or dividing p minus 1 if p is odd and order 2 if p is 2. And then the whole point is if you use the sigma character to let it act constantly, you're effectively forced to raise it to an integer power. Right? I cannot take something that is essentially a random zp star and raise it to something that is not an integer. So then if you realize this, then you should say that this here, this diamond character, is close to 1. So that means I can actually base this 2 elements in ZP because it will converge and I get a sensible number of it. The thing that obstructing this interpretation is this character of finite order. This is, as I say, order dividing p minus 1. If you look at, for example, interpolation formulas, etc., you always see this congruous condition p odd and then the same always modulo p minus 1. And once you remove this one, then you have a lot of freedom because this simply takes any, well, not any, but this will take many p-adic powers to raise to. So then you have a lot of freedom. Right? So it's not just a notation because it really changes. I was trying to explain in the proof of, for example, here. right? If you look at your p-adic alpha function, there the argument is automatically p-adic. Right? You take this q0, which is close to 1, you base it on 1 minus t, and then minus 1, you plug it into some p-adic fallacy. So this is all completely p-adic. And therefore, if you take the regular Tate twist, you're sort of stuck to twist of an integer. And this one always exists. And this is also, I think, maybe the first time you really see an interpretation of the zeros of your p-adic alpha function. And because if I have a p-adic alpha function which is 0 here, then both the h1 is going to be infinite and the h2 is going to be infinite. And then you actually get some statement here about the rank. If this mu becomes positive because we have a 0, then this minimum is at least equal to 1. So it will be 1 in practice. So our 0 is often 0. And then this will be 1, 2, 3, etc. And this will be 0. It means your R2 will be solid to 1 in the order. Let's say you altered the equality models. Right? And if you don't, if you look at this one, you have a 0 for your p-adic alpha function. You cannot interpret that in this thing with normal Tate twist, because then you're stuck to give them an integer. And for general p-adic E, this is just remotely like normal Tate twist. So you at least can see, because this is not a homology that people usually study, but it looks very natural in this context. Okay, so it's more than just a notation. Plus, it simplifies all the Coates norms. And so I really want to make a case that this is the way to go on the p-adic side, and then if you want to get back to maybe more real life, then this is what you do. You sort of say, oh, this is the thing, or this part up to here is purely p-adic. The p-adic alpha function valuation, that was sort of characteristic, and that's involved only a 0 h1 with those modified Tate twist. And I could have written this for n replaced with little e, p-adic argument. And then here you use that n is an even, it's actually an integer, and therefore I can rewrite the character in the representation underlying this with this funny diamond twist. I then need an integer power of the type of the character to change this into normal Tate twist. And that's exactly what's going on here. And that is to go from the p-adic interpretation here, using p-adic alpha function, back to sort of maybe more classical twist. And then the funny thing is that the same thing happens in the interpolation form. And I actually don't understand why this is exactly the same power of time character, because it's not obvious to me that it should happen, but it does work. So I think this must mean something that either your p-adic diamond twist p-adic alpha function, or you switch for your classical alpha function, classical Tate twist, and your character changes with the same power of the time character. So it's definitely more. It's really, I think, the way one should work on the p-adic side. And then some stations say, hey, we also have a non-p-adic side, let's throw in some time character. Let's go to a regular Tate twist. Because everything we do is basically entirely p-adic, except for a few applications where we suddenly say, okay, let's now go to classical Tate twist. But I think that another, what I say, is really interpreting zero to p-adic alpha function, you have to work with this time system.
Not understand.